Hi, and welcome to Module 4 in Lecture 14. In the previous module, we dealt with the Jacobian matrix, which allowed us to take the derivative of a vector-valued function of more than one variable. However, that was still a bunch of first derivatives, right? If you think back to the stuff we did in the very end of part 2 of the course, when we started trying to optimize functions, it was helpful to understand the second derivative, because that told us information about the curvature of the function, which helped us understand if we had a minimum or maximum or a saddle point. Well, now that we're in multiple dimension land, right, now that we have multiple variables, we still might want to know about the curvature of the function in these multiple dimensions to serve the exact same purpose. When we're trying to optimize in a multidimensional context, we want to understand how the curvature of the function in more than one dimension, because that will serve the exact same purpose to help us understand if we have a maximum or minimum or a saddle point. So we're going to have to understand higher order partial derivatives. The good news is they're the same as higher order regular derivatives, right? So higher order total derivatives. So remember before we could write this would be the second derivative. Well, this is the second partial derivative, and it's computed in the same way. So if we had a function x squared y, the first derivative would be 2xy. The second derivative you'd obtain by taking the derivative again, just like you did before when we took the second derivative of for the total derivative in one dimension, still keeping y constant. So the second derivative of this thing would be just 2y. The x is gone. That's how it works. Second partial derivatives work the exact same fashion as second derivatives. In the one-dimensional case, you just take a derivative of a derivative, right? So this is the same thing as the derivative of the derivative of x. You do it twice. And again, since it's a partial derivative, each time you hold all the variables constant. And that's mostly it. And you can go higher than this too. You can do third derivatives and fourth derivatives and so on. But first and second derivatives occur much more often than higher order partial derivatives. So these are the ones you'll be dealing with more often. That said, calculating third derivatives and fourth derivatives is exactly the same. You just keep doing the same thing over again, right? So the third derivative would just be the derivative of the second derivative, and so on. Now the notation can get messy sometimes, so sometimes we just, like we did in the previous one, we just write this for a first derivative, this for a second derivative, this would be a third derivative of the same variable, or we might just simplify even further and just call this the function, so this would be of f, or we just have this. When you subscript a function, it typically, with a variable's name, it typically means take the partial derivative of that function with respect to that variable. But these are all just different notations you might see. The more general sort of common notation is this. So that's the derivative of the notation. Now what I've left out here is an important case, which deserves its own little section, which is what happens when you take a derivative of two different variables. So for instance, what if you take first the derivative with respect to x, and then the derivative with respect to y? So first you're going to treat everything else constant and take the derivative with respect to x. Then the answer for that one, you differentiate, and then take the derivative with respect to y, treating the x constant now. So as an example, if we had x squared y, right, first we would take f, the partial x, and that would be 2xy. Now we would take partial y of 2xy, which would treat x as constant now and differentiate y with respect to y, which would give us 2x. So this thing would be 2x in that case. Now, what if we change the order? What if we did y first? What would happen? Well, let's do it. Well, again, we start at the beginning. Now there's an x squared times y. So first we do y, and we get x squared, because x squared is the constant here. And now we differentiate with respect to x, and we get 2x, and lo and behold, it's the same thing. This is a general property, which makes life easier for us in a bunch of cases, as we'll see. That is always equal to this. And we can actually write these things in a more compact form. And this is always going to be the same thing as this. In other words, it does not matter what you put in the bottom. These things are called equivalently either mixed partial derivatives or cross-partial derivatives. Or just cross-partials for short. They end up being very important in a bunch of contexts because they have an important substantive meaning. Right? If you go back to we talked about it for first and second derivatives, the first derivative tells you the rate of change of a function. The second derivative tells you the rate of change of the rate of change, or the acceleration, right? How fast the function is changing. Right? Not just the rate of change, but how fast that rate of change is changing. And that gives you the curvature of the function, and therefore it's an important factor here. Now, for mixed partials, something different. Now, for the standard regular partials, so for instance this up here, right? That means the same thing. It's how fast the function is changing. It's how fast the function is changing in one dimension. So these things give you substantively whether or not your function has, say, decreasing marginal returns or increasing marginal returns substantively. What about these down here in red now? Right? These cross partials, these mixed partials. What do they tell you? Well, they give you a sense not of decreasing or increasing marginal returns to that variable, to your function, but rather of complementarities or substitutabilities. Right? If the cross partials are positive, then increasing one variable, x, increases the rate of change of the function in the other variable. In other words, increasing one variable makes the other variable have more of an effect on the function. And that's true in both directions. If you increase y, then x has more of an effect on f. If you increase x, then y has more of an effect on x. That's what happens if x and y are complements in a sense. Increasing one makes the other one more beneficial for increasing f. The language here comes from making f a utility. You're trying to increase your utility in general, so increasing x makes y more valuable for increasing your utility, and vice versa with y and x. You've already actually seen a little bit of this. I'll keep this on this page because it's important. When we dealt with interaction terms in the previous lecture, we said the first derivative, and I don't have room here, the first derivative, I'll try to write small, was beta 1 plus beta 3x2. Well, what's this cross partial here? Well, now we can differentiate this partial derivative with respect to x2. We're left with beta 3. So the cross partial is beta 3. So here, beta 3, the coefficient on the interaction term, tells you whether these two things are complements in the sense that increasing one makes increasing the other one more effective in increasing y, or substitutes. Now, a substitute is when the beta would be, so a complement is when the beta 3 would be positive. A substitute is when the cross partial, in this case beta 3, is negative. And that means increasing x makes increasing y less effective, right? Less effective in increasing y. Sorry, increasing f. Apologize. Let me say that again. Increasing x, if it's a substitute, makes y less effective in increasing f. Right? So x substitutes for y. Once you have x, y is less beneficial for increasing your utility, for instance. Those are substitutes. So the cross partial encodes a lot of useful information about whether or not these two variables are complements or substitutes. And that ends up being really important in game theory. There's this whole technique in game theory called monotone comparative statics, which lets you get really nice, clean results out of various game theoretic models by focusing largely on whether or not the utility function has complementarities in its inputs or substitutes in its inputs, or neither. So there you go. And not all functions have always complementarities or always substitutabilities. So it can depend on what point you're at, right? As before, these cross-partial derivatives are functions, and they might vary in sign by what point you're at in the function, right? By what point you are, what x value and what y value. Things have complements uniformly if they're always if that cross partial is always positive at all points, and substitutes if that cross partial is always negative at all points. So there you go. So there's sort of the meaning behind these cross partials, and that gives you a sense of how to take higher order derivatives and also cross partial derivatives. And that gives you a sense both of how you use these, how you compute second order derivatives, both the ones along x squared, say, so partial squared f, partial x squared, and also the cross partial or mixed partial derivatives, and where they're used for, and how they're used in things like game theory and understanding complementaries and substitutabilities, both in game theory and also in statistics when you're trying to understand, say, the interaction term coefficient on your linear regression model. But there's more to it than that. And we said before, the primary use of these second order derivatives is understanding the curvature of your function when you're trying to optimize your function. Right, as we did way back in part 2 of the class, part 2 of this course, when you're trying to, if you have a critical point and the curvature is negative, so it's going down, you have a maximum. If it's positive, you have a minimum, and if it's neither, you have a saddle point. You can have a saddle point there. Now, in more than one dimension, you can do the same thing, and the curvature of the function serves the same role. It gets a little more complicated. So the first thing we need to do to use this is to put all these second order derivatives together, and we do that in what's known as a Hessian matrix, H. And this H is quite often called a Hessian by itself. This is primarily confusing only because this Hessian is not the determinant, right? The Jacobian was the determinant sometimes. The Hessian matrix, or the Hessian, is always the matrix itself. We generally use the matrix and not its determinant. Well, we do use determinant too, but we generally use the matrix as well. Okay. The Hessian. What's the Hessian matrix? Well, the Hessian matrix has components. These are the components. And each one of these components is the second derivative, second order partial, with respect to the component xi, can I draw the finger, and xj. So if I equals j, then you have diagonal elements, which are just these derivatives. And if I and j are different, then you have cross-partial derivatives. Note that because the cross-partial derivatives are equal, no matter which order you do it in, for this matrix, for this Hessian, hij will always equal hji, because it doesn't matter what order you take derivatives in, and therefore the Hessian is always a symmetric matrix. This will come in handy in the next lecture when we try to use it to figure out whether or not it's positive definite or negative definite, because it turned out that understanding if the curvature is effectively positive, right, will be related to, well, if it's curved down, right, negative, it's like negative definite. If it's curved upward, it's positive definite, and it has similar associations with maxima and minima as before. We'll do a little more of that in the very last module of this lecture when we discuss concavity and convexity in more than one dimension. We'll associate it with the Hessian in that same way. So I don't want to give away the whole thing now. But the point is the Hessian captures the curvature of the function in more than one dimension. Okay. So that's the Hessian. So you can put it together, and if say you had there's a 3x3 example in the book, but let's do a 2x2 here. You could write it like this. So here's your f dx 1 squared, t squared f dx2 squared, t squared f dx1 dx2, and the exact same thing down here, which helps in the sense that we don't have to actually calculate every element, just basically the upper triangular or the lower triangular version of this. Let's do a quick example of that. If f is going to be x1, let's go back to this one again. We already said that the cross partial of this thing, sorry, it's be x1 and x2, was going to be 2x1. That gives us the off-diagonal elements. Now, what's the second order derivative with respect to x1? Well, you do it once, you get 2x1, x2, treating x2 as constant. You do it again, still treating x2 as constant, you get 2x2. So this is 2x2. You take the derivative of the x2 once, you get x1 squared. Take it again. Now there's no x2 at all, so it's just a constant with respect to x2. So the second derivative is 0. There you go. There is the Hessian matrix for this function up here. There's a little longer example with harder derivatives in the textbook, and obviously you can go to the problem sessions and do more too in the problem sets. But that's all it is to how to calculate a Hessian. So it covers almost everything we're going to cover here. We'll deal more with what the intuition behind the Hessian is in the next module when we discuss curvature. But one last thing I want to mention is, yet again, we can call upon the Taylor expansion to give us an idea of how this works. Let's go back for a second. And by the way, if this is confusing, I personally find the Hessian more sensible than the Jacobian in the sense that it has a nice symmetric nature, and that's good. With the Jacobian, you have to remember that the rows are each components of the function, and the columns are different variables. But if you like the Jacobian better for some reason, basically this thing's the Jacobian of the gradient. But one last thing, we can go back one more time to the Taylor expansion. Taylor approximation to this thing, right? We said already was going to, around the point A, would be FA plus the gradient of F evaluated at A dotted with this vector. But now if we want to go to higher order terms, say second order terms, to incorporate more of the curvature of the function, to get a better approximation, and this is an approximation, you could do this. Transpose of those column vectors times the Hessian evaluated at A times the column vector here. And this thing gives you this row vector times the square matrix, which is always square, the Hessian's always square, times the column vector will give you a scalar. And this gives you a closer approximation to the function before. And this gives you a better sense, again, of what the Hessian means, because this thing tells you the curvature of the function sort of locally around that point, at least to a squared order. And that's it. There you go. That ends the talk about the Hessian. We'll see with the Hessian again a little in the next module, and again a whole lot in the again some in the next lecture. Thank you very much.